We thank the organizers' invitation to this documentary symposium. My name is Yong Yang. I will be talking about recent results and the status of PandaX documentary experiments. So this is my talk outline. First, I will introduce the China JinPing underground lab and the PandaX documentary project. Then I will present the latest search results with the full exposure documentary dataset from PandaX-II detector. After that, I will present the progress and the status of our next generation experiment, which is PandaX-IV. So PandaX is a series of xenon-based particle and astrophysical experiments. The collaboration was formed in 2009 with roughly 50 people from China, US, France, Spain, and Thailand. The experiment is located in China JinPing Mountains. The laboratory with more than 2,000 meters of rocks above is the deepest one in the world. So this place is really a good place for rare events detection. The construction of the second phase of the lab is also started since last July. After completion, the lab will also be the largest one in terms of available space. So this is one slide to show you how the dark matter detector works. So this is a typical dual phase TBC. So in one event, we will have S1 signal from the liquid and S2 signal from the gas. Using the time difference between the two signals and the light pattern of S2, we can pinpoint the street location of the event vertex. Moreover, using the ratio of S2 and S1, we can tell the characteristic difference between nuclear recoil and the electron recoils. So starting from 2009, the PandaX collaboration has completed 2 experiments for dark matter search, PandaX-I and PandaX-II. Right now, we are preparing for the next experiment, PandaX-IV. Meanwhile, we have also another experiment, which is PandaX-III, that will use high pressure gas TBC to search for zero neutronics double decay detection. So we have completed the PandaX-II data taking. For the final main analysis, we have 130 ton-day dark matter exposure. This table summarizes the background contribution and the observed data from different periods of data taking. Overall, the prediction matches with the data. For the final limit setting, we used 4-dimensional PDFs to describe the background distributions. For those events below the nuclear recoil medians, which are the most interesting events, we also studied the relative likelihood for each background and also a dark matter signal with mass 400 GeVs. For instance, for event number 1 and number 2, the highest probability is from either due to a dark matter signal or from the accidental background. So this is a limit from our final analysis. This is the red curve compared to the results we released in 2017. The search sensitivity in terms of the median of the search sensitivity improved by a factor of 2. The observed limits lies within 1 sigma of the sensitivity band for WIMP mass above 10 GeV. Below that, we do see there is some local downward fluctuation in the data, so we have to constrain our limits to be the 1 sigma of the sensitivity band. So using the same data set, we also performed axion searches, which expect to produce electron recoil signals in our detector. The event stacking is quite similar to the dark matter searches, except that we expanded the energy search window from 10 keV to 25 keV. We also reduced the fiducial volume in order to suppress the wall backgrounds. All critical backgrounds spectrum, including the tritium, the krypton, the radon backgrounds, have obtained using the calibration data. You can see the agreement between the simulation and our data distributions. Except the tritium, all other backgrounds have also independent control using non-single regions in data. So using this low energy events from PandaX-II, we can perform independent search for possible access, which with xenon one-ton publication recently, if we assume xenon one-ton based phase signal is complete due to action events, we would expect PandaX-II detector to say about 21 events. This is shown in the dashed curve in this left figure. This is also the background only fit to our data distribution. Instead, if we fit our data using backgrounds plus single, we would obtain about 22 action events. But the error bar is also quite big. So the number is both consistent with long hypothesis and also with xenon one-ton observation. We just need more data to tell. Therefore, we derived the upper limits on the solar axion electron coupling constant, which is shown in the red curve in the right plot. So that is all for PandaX-II. Let me move to PandaX-IV in the next few minutes. So the experiment is in the new B2 hall in CJPL2. The infrastructure was completed in last August. And since then, all subsystems moved in, and now the installation has been completed. This photo is the inside view in the middle. And below the surface, we have a water tank with about 900 meters in space. And the ultra pure water will share the background from the outside environment background. So this is just a number of pictures to show you the subsystems during the installation, which I will talk about some of them in the next few minutes. First, for the cryogenics, the cooling power is designed to have more than 300 volts. During operation, we will have at least 2 cooling heads. And this system is capable of liquefying 0.7 tons of xenon per day. We will also have online purification to remove the impurities that comes out from the outgassing of the detector materials. The expected flow rate will be about 100 standard liters per minute. So we have also built the destination tower to remove the krypton and radon. The design goal is to reduce the krypton level to 0.1 ppt and the radon level to less than 1 microbake per kilogram. We have successfully commissioned the tower. We have also measured the krypton level to be less than about 10 ppts using the RGA plus a cool trap system. This is also the limit of the system. During the online distillation, the radon can be also removed. So at this moment, all the PMTs have been installed on the TPC. Before installation, each PMTs was measured at both room temperature and low temperature. And this plot shows the rate of the dye current at room temperature, which is about 500 hertz. And this will reduce to only 20 hertz at low temperature. The average gain of the PMTs is about 5.5 millions. That will be correspond to several millivolts in terms of amplitude if you look at the signal in the oscilloscope. The average after pulse probability is about 1%. So talking about electronics and DECO systems, the whole system is completely new and many aspects have been improved compared to PandaX-II. For instance, the number of channels increased by a factor of 3. The sampling rate of the flash ADC is increased from 100 megasample per second to 250 megasample per second. Then we will have a more precise reconstruction of the waveform from PMTs. In PandaX-II, the data taking also relies on a global external trigger, which is primarily for large S2 signals. In PandaX-IV, we don't need such external trigger. Each channel can be triggered dependently using a self-trigger threshold. We will also have more DECO servers to read down the data, so the bandwidth limit is improved by a factor 10, as you can see from this plot. This is from the IRD calibration with the 50 Hertz extra trigger rate, but we just manually increase the number of samples per segment per trigger. So we see the bandwidth increase nearly, and at about 1 gigabyte per second, the DAQ start to saturate. So as I mentioned, we don't have the external trigger during normal data taking, but we still have to zero separate the baselines, because most of the time the signals from PMTs are just baselines. This is illustrated in the this plot from the KN digital manuals. So to study this, we took some data without applying the zero separation mechanism in the digitizer, using the LED calibration runs. So you can see in this figure, we can see both the pedestal and the SP signals if we integrate the fixed window of the waveforms. So on average, if we set the trigger threshold to be 20 ADC counts, which is about 2.5 millivolts, the 3-inch PMTs will have on average SP efficiency about 98%. And this is currently our default setting for the DAQ configuration. So at this moment, our detector is closed. We have took some data in dry environment, and the PBC was fed with 1.5 bar of gas xenon, and all the PMTs were turned on. You can see in this, this is a charge pattern of the top and bottom PMT arrays. And this is actually from high energy events, probably due to alpha events. And this is the waveform with this candidate, with the weights about 300 nanosecond. So this is like a large S1 signal in our detector. So in a summary, the PandaX-II experiment has completed its mission. We have completed the full exposure analysis, the dark matter search with a factor of 2 improvement on the WIMP search sensitivity. We also performed axion searches using low energy electronic data. We have made steady progress on next experiment, PandaX Photon. Right now, all subsystems have been installed and being tested in the B2 of the CJPL2 lab. We have taken some dry runs to test the TPC and plus PMT and the DAQ system performance. So we expect the real data to come very soon. So please stay tuned with us. Thank you very much.